All right, good day, everyone. Welcome to our webinar presentation. My name is Adam Harris, Managing Director here with C-Therm Technologies. Very pleased to have on the line with us Sarah Ackerman. Sarah is head of our application development group and contract testing lab. She's an expert in transient-based thermal conductivity methods. She's going to be walking us through the work done specific to geological samples. And that's really the main focus of today's webinar. Titled Rock On, How to Characterize the Thermal Conductivity of Geological Samples. This presentation should run for approximately 1 hour. We've got a lot of information to cover, so we'll get going quickly on it. I want to provide just a little bit of background on us as an organization. So I see a lot of familiar faces on the participant list for this webinar, but there's some newer faces too. If you don't know us, we are niche specialists in a very specific area of thermal analysis, and that's really in the characterization of thermal conductivity. What we do exceptionally well. In fact, I would argue we're the best in the world when it comes to contact-based transient methods for thermal conductivity. Our goal in life, our raison d'etre, is to simplify the characterization of thermal conductivity and to drive improvements and innovation in this field to make it easier to take these measurements, to get you better quality data under better representative conditions for your given application. And there's a lot that we'll talk about in the context of geological applications that really do present some interesting dynamics and challenges to some of these measurements, which we really excel at. And I'll point to examples such as testing at high pressure conditions, elevated temperature conditions, dealing with a wide variety of sample formats. So lots for us to share in that context. A quick overview of our product lineup. It's good just to have a little bit of familiarity with what options we're going to be referring to in this webinar. Starting at the left, we have the TC kit. This is our most economical offering. It's really oriented towards academic researchers that might be more challenged in terms of accessing significant budgets for research equipment. It provides a great tool to kind of get in the game in terms of being able to generate some thermal conductivity data. There was a nice webinar Sarah referenced just before we started the recording, really walking us through the background of this kit and what it can and can't do. It uses the same type of flex TPS sensor that's available on Trident that we'll be talking about. Trident is the product in the middle. We'll be talking about use and application of the flex transient plane source, or sometimes called hot disk sensor. This is the same type of sensor, but on Trident, we incorporate it with a better support package to provide a broader dynamic range. It meets the ISO standard as it's implemented on Trident. And when you move into the Trident class of instrumentation, you're really getting a research grade instrument. The temperature ranges are wider, the sensitivity is better. And with Trident, you have the versatility to have 3 different test methods with the same instrument. And that's going to be, the value of that is going to be really apparent as we start to get into the geological set of applications where you've got soils, you might have fluids, you've got hard compacted materials, very rigid samples, a wide variety of formats that it's really helpful to have that versatility. On the far right, I'll mention it just in passing. It's called a TX Touch Experience Platform. This is really more used in the area of textiles to quantify thermal touch from a warm feel or cool touch perspective. I don't see many folks from the textile industry online, as we would expect. That this is really an audience more focused on geological applications. But if for some reason you are interested in geological, or rather textile applications, the TX Touch Experience Platform is very interesting, and we have a webinar coming up, I think, in about 10 days on that as well. Could be of interest. I want to start just with a really interesting client case, and this is an example from geological surveying. So this is a situation where a client of ours in Atlantic Canada, and most of our clients are further abroad throughout the U.S., Europe, Asia, are our main markets, but we do have a really interesting user case here more locally in Atlantic Canada with C-Therm Geo Surveys. So they've invested in one of our systems, and they actually take it out on their surveying boats. They have a mobile lab unit where they're extracting samples from the under the Bay of Fundy, and they're testing those samples on the boat. It's important to do that quickly because the samples will dry out if you wait to get back to shore to test them. So this is just a really interesting user case, and there's a nice comment here from the president of C-Therm Geo Surveys, commenting that they turned to the C-Therm instrument for effective thermal conductivity characterization in our exploration vessels onboard lab. The portability and ease of use of the instrument allowed our technicians to rapidly measure thermal conductivity of our geological core samples accurately and consistently in a 24/7 operation. As a Nova Scotia-based company working worldwide, we were pleased to have a local, made in Atlantic Canada solution for our project requirements. We would recommend the TCI for any research or screening with a focus on geological and/or in situ applications, and we will continue to utilize it on new exploration missions. So that's just a nice reference testimonial from our client, David Lombardi at C-Therm Geosurveys. If you're interested in other client testimonials, I'm going to ask Stuart or Anna to just drop in the chat box a link to where you can find a whole list of different client references. There's a testimonial page available on our website, and if you're interested in checking any of those out, you certainly can. It gives you certainly a sense of the variety of different clients and their experience in working with us. I didn't give them a heads up I was doing that, so I'm hoping they can find that without too much difficulty. So Sarah will be highlighting really the different tools available within Trident. This is one instrument platform that offers 3 methods for thermal conductivity. And our philosophy here is it's better to have options. We've got the Flex transient plane source sensor. Sarah will detail all of these in terms of how they work and what they can do, but also what they can't do. We're going to try to give you a very sound foundation in terms of understanding of what these tools can do and can't do. The needle probe is sheathed in stainless steel. It's very robust. That's the one in the middle. And then the MTPS, you'll see heavily profiled in this work. It's a very innovative design that we've developed. It's a single-sided sensor. It's the only single-sided sensor that has what we call guard ring technology, which ensures a one-dimensional heat flow into the sample material. Very important from the perspective of measuring samples from a single-sided sensor. So Sarah will talk a little bit more about that in her section. But philosophically, to kind of understand the value proposition to this product, I really like this quote from Abraham Maslow. So you might remember Maslow from your organizational behavior coursework in university, or if it's something you study. But this is a quote that really, I think, captures the value of Trident. And that, often when we're used to only one tool, we apply that tool to all situations. And obviously there are situations where perhaps other tools might be more beneficial. So the quote is, when all you have is a hammer, everything looks like a nail. And so when we only have one thermal conductivity method, each method has its own certain orientation or bias. You can get into some problems in applying it in situations which it was not really designed for. And so this is all part of what we want to convey in the presentation, is educating on what the appropriate applications are for the different types of test methods in thermal conductivity. Okay, so this just gives you a sense of the relative size of the sensors. So the active area of the MTPS sensor, this is the one with the guard ring technology, is about 18 millimeters in diameter. That's the active area of the sensor. The Flex TPS sensor comes in a variety of different sizes. 6, 13, and 30 millimeters. So if you're looking at different scales that you want to alter, the TPS gives you a lot of flexibility. That's part of the reason we have it in the name, the Flex TPS sensor. It's also flexible. It's a nickel foil encapsulated in Kapton polyamide. So it's a very flexible sensor, great for really rigid samples, and Sarah will detail this further. The needle probe, needle transient line source, very robust, great for soils. You'll see this featured in the application section. It's the longest sensor. It's 150 millimeters in length. Something that's very unique to us that I think is really interesting, and you'll see in some of the content Sarah will present, is our unique accessories, and specifically the high pressure cell. So we actually have a range of high pressure cells. This is one example of it. We have them for solids. We also do a different variant for liquids. Testing at elevated pressure conditions is really important to understanding the effective thermal properties for a given application. When you think about what impacts thermal conductivities, temperature, pressure, humidity, all have a significant impact on the effective thermal conductivity. And what we really try to get people thinking about is to ask yourself the question, why am I measuring this thermal property in the first place? Often we're trying to model it from a process optimization or process safety perspective, or it's an underlying characteristic that's very important to the ultimate performance of the material. So important to really represent those conditions in the testing of the material. You can get some very non-representative data if you do not pay close attention to some of the environmental considerations, how the sample is oriented, the environment in which you're testing it. If you don't watch those things carefully, it can really impact the quality of your data. Okay, lastly, just before I hand this off to Sarah, this slide just summarizes the nominal ranges for the different methods. So I'll leave this on screen. I'm not going to go to it in great detail. You can kind of read across and see how those relate. But at this point, Sarah, I'm going to ask you to bring up your slide deck, and we'll transition into your section.
Okay, I will do that.
All right, and I'm going to drop off the cam and mute my mic, and we'll let you take it from here. I'll rejoin you for the Q&A session.
Sounds good. Okay, so talking about the thermal conductivity of geological samples, it encompasses a very wide range of material phases, degree of purity, and other factors. So it's a very complex field, and therefore method selection becomes really important. So that's where anybody who has any interest in geological materials, we would very strongly recommend you to take a look at the method selection guide. Make sure that you're choosing the right material test method for your samples. We'll look first at some applications that are appropriate to the modified transient plane source method, or MTPS. That uses the sensor that you see here in this slide. So this is a calibrated sensor. The measurement takes place on the green chip that you see in the image there, using a modified transient plane source method. So it measures the thermal effusivity and also the thermal conductivity. When you're running an MTPS test, the measurement works in a pretty straightforward principle. You place the sample on top of the sensor and apply a heat pulse through the sensor spiral, which is the heating coil, the spiral in the center there. And simultaneously with that, a guard heater called the guard ring surrounds the sensor spiral. and you heat that as well to prevent any lateral temperature gradient from forming. So you don't have any lateral heat losses, and therefore you're looking at the heat transfer basically in the direction perpendicular to or normal to the sensor surface. We make the sensor spiral out of a material that has a very high temperature coefficient of resistance, or TCR, and therefore we can calibrate the voltage drop across the sensor spiral to the temperature of the sensor spiral. Therefore, by monitoring the voltage as a function of time, we can look at the sensor temperature as a function of time and then analyze that data to get at the thermal properties of the material. Of all of the methods that we're going to be highlighting today, this is the easiest to operate because all of the data analysis is fully automated in the software. Looking at the first highlight, we're looking at thermal conductivity of crude oil under pressure. So this is using one of our high pressure cells accessories, designed specifically to look at thermal conductivity of volatile materials above their typical boiling point or approaching their typical boiling point to prevent too much evaporative heat loss. So the goal of these kinds of work is to see if the thermal conductivity is different between different sample materials, between different oils, for example, or different extracts, and also to observe the effect of temperature on the thermal conductivity of the oil at a constant pressure. This becomes important looking at the thermal management of, for example, oil pipelines to make sure that you're providing enough heat to them so that they don't start to approach their wax appearance temperature, as one example. So when you're looking at two different, we have two different materials here, and on the x-axis here we have the temperature. On the y-axis we have thermal conductivity. Sample 1 increased slightly in thermal conductivity and then followed a decreasing trend, whereas sample 2 consistently followed a decreasing trend, and actually sample 1 and 2 had effectively the same thermal conductivity at the highest temperature point here. This can be used to, again, model process thermal management, but it can also provide insight into the process efficiency and perhaps the purity of the end product. Looking at our application highlight number 2, this is again looking at elevated pressure testing using our high pressure cell range of accessories. So the one for solids you can see on the right hand side in that image there on the slide. For thermal conductivity of solid materials, pressure can play an important role if the material is, for example, if it's porous, or if it is in some way compressible, so that its properties might change as a function of the pressure of its environment. So therefore, we can control the pressure of its ambient environment and see how that affects the thermal properties of the material. So this is looking at kind of an oil sand type of core material. Looking at the red line is under 2000 gauge pressure of gas, and the blue data set is looking at basically ambient pressure. And you can see obviously here, even at the same temperature points, the applied pressure does have a significant effect on the thermal properties of these samples, which is a very good example of why making sure your testing conditions are representative of the sample's actual environment can be very important in terms of making sure you're working from reliable data. looking at highlight number 3. So this is looking at basically an exogeology application, some work out of Stony Brook University, their Department of Geosciences. And specifically, they were looking at the thermal inertia and the thermal conductivity measurements of rocks designed to be analogous to Mars rocks, to help understand the thermal behavior of the kinds of rocks that you'd be likely to see on Mars, and potentially aid in design of future developments for Mars exploration. So thanks to NASA's missions to Mars, we're starting to learn more and more about the geology of Mars, and understand basically its history in a geological timescale, but also the geochemistry of the sediments and rocks that you find on Mars. But right now, it's not really completely clear how the conditions on Mars affect the thermal properties of the samples and rocks found there. So this work was done to characterize how a Mars-like atmosphere and pressure might affect the thermal properties of a material, in this case, rock samples. So the test setup looked like this. So they have another pressure cell, which they've called their Mars simulation chamber, over on the right-hand side here. They've got pressure gauges and relief valves, the ambient pressure TCI sensor, their vacuum pump, which they use to create the low atmosphere inside of the cell, and a control console for their vacuum pump. And they can characterize here the thermal inertia of the rocks, or their thermal effusivity is another word for that property, relative to the sample porosity. They can also perform a similar exercise with thermal conductivity. Looking into the fourth application, we are looking at geothermal mapping. So a very common application for thermal conductivity measurements in geological systems is looking at geothermal heating technologies, whether it's the near surface geothermal resources, or some of the deeper geothermal resources that can be exploited. So specifically, this paper that we're highlighting is work from Dr. Eloisa DeCipio, and it looks at shallow geothermal resources. So shallow geothermal resources are usually those that might be exploited by ground source heat pumps to provide heat in the wintertime and cooling in the summertime. Generally speaking, shallow geothermal resources are the kinds of geothermal resources that might be exploited by a residential property owner. Usually for the more industrial level applications, you'll get into some of the deeper ones from what I've read. When you're looking at geothermal applications, higher thermal conductivity of the reservoir material gives better heat transfer efficiency in the heat pump system, which in turn leads to better geothermal performance of the heat pump. So these slides, the next few slides are basically taken from a presentation that Dr. DeCipio presented originally at NATAS 2017, and it's also available on an earlier webinar. So I'm going to go through them fairly quickly, and if you'd like to see them in some more detail, our moderators can provide a link to those, to the original presentation of this material. So specifically, she's her work was looking at shallow geothermal resources evaluation and the assessment of the thermal conductivity values for rocks and other unconsolidated materials, both by published data, reviewing the published available literature data, and also looking at direct measurements both in dry and wet conditions. That's especially important when you're dealing with unconsolidated materials because moisture content will have a very large effect on the effective thermal conductivity of unconsolidated geological samples. The goal of this was to establish a regional database and map basically of the thermal conductivity of geological materials in the region of Italy that was studied. The aim of this mapping exercise is specifically to look at good geological potential for geothermal building conditioning, basically. If you can identify regions which have favorable thermal conductivity in the region, you can then build yourself a potential map and identify regions that have a very good potential for high performance of these kinds of geothermal heat pumps. The reason why you have to do this kind of a sampling and empirical mapping exercise is that actually geothermal reservoir conditions, their thermal conductivity can vary quite largely based on the minerals present, the bulk density, and the water saturation, as you can see on this slide here. And there's many different many different variables in terms of what governs the behavior thermally and chemically of the rocks in the reservoirs. And therefore, it has to be a kind of a semi-empirical type of method that you follow to build these exchange maps. So you can test the thermal conductivity of these various materials as a function of material porosity, of the moisture content, and also of the temperature, which can then be used to build maps. So this is the kind of test results that her group was able to publish in Geothermics in 2020, just a month or two ago, actually, was when it was officially released. They completed the building of a geothermal database for geothermal potential evaluation. So on this slide, you can see thermal conductivities of various types of stone and rocks materials. And the ones with the colored bars are ones where the thermal conductivity was experimentally measured in this work. You can then take this kind of data and use it to build this kind of a shallow geothermal exchange map that I've been talking about previously. So the heat map that you see here shows the relative attractiveness for geothermal heating applications of different regions. So you can see the areas that are more blue in appearance have the higher potential for geothermal exchange, and the areas that are more white have a lower potential, and everywhere in between kind of has various colors in between there. The fifth highlight is looking at some work we did in our application lab, looking specifically at geological research samples, the sandstone, dolomite, and limestone. So you can see on this slide the test setup for testing these kinds of materials. It really is quite straightforward. You place the core sample on top of the sensor and then place a weight on top of the core sample. And that will give you the testing setup for MTPS testing of these kinds of materials. And you can identify that the higher porosity material here, the limestone, has the lowest thermal conductivity, which is as you would expect for that kind of a trend. And the most consolidated of the three samples also had the highest thermal conductivity. Again, this is exactly as you would expect. Now that we're kind of done highlighting the sorts of applications that the modified transient plane source is appropriate for, we'll look a bit at the transient plane source method. So this employs a double-sided flexible sensor, which is why we call it the flex transient plane source sensor. And some of the advantages of this method is that the contact resistance is dealt with by exploiting the symmetry of the testing setup, and also by basically removing the portion of the data that is affected by the thermal contact resistance. So you don't need a contact agent to get valid data, which is useful if your material is, for example, highly hygroscopic or very porous, and therefore it would absorb most common contact agents. You can also look at some specialty application modules like the slab module and the anisotropy module for samples that maybe don't have the ideal sample dimensions for some other methods. So it can be the most flexible material or test method, but it also requires the greatest user expertise and the greatest degree of user experience and time to work up the data. The two properties measured by this method are the thermal conductivity and also the thermal diffusivity of the material. By looking at the thermal diffusivity of the material and the thermal conductivity, you can get an idea of the heat capacity of the material as well, although it won't be quite as accurate as you would get, for example, if you were using a calorimeter. One of the reasons why we call the flex method flex is because of the range of sensor sizes available. So rather than kind of trying to force your sample to conform to the sensor size, in this case, you have the flexibility of choosing the sensor size that fits the sample. The smallest sensor size here is appropriate to very small samples. And the largest sensor size there is 30 millimeters in diameter, and that would be appropriate to materials which tend to be highly heterogeneous. So, for example, if you were looking at a volcanic tuff with a lot of different sizes of materials that are kind of consolidated into that tuff, that would be a case where the large TPS sensor might be the most appropriate. The sensor in between it is our 13 millimeter TPS sensor, and it's kind of the workhorse of the TPS sensors. When you're running a test, all three of the sensor sizes operate on the same principle of operation. You sandwich the sensor in between two identical pieces of your sample. And then you run a scouting run, and you do that based on some predefined power and time parameters based on what your material is most like. So for most consolidated geological samples, you're going to choose recommended time parameters for ceramic-like materials because those are the most thermally similar to rocks and other consolidated geological samples. After you run your scouting run, you're going to, or the software basically is going to analyze the first temperature versus time curve and report some preliminary data. And you use the preliminary data to optimize your time and your power parameter selection and rerun the test. And after a couple run-throughs of this, you can zero in on the ideal time, power, and sensor size to get a very good quality measurement of the thermal conductivity. This iterative procedure is a little bit time consuming and does require a fair amount of user expertise. So we're looking at porous geological materials, which are the kinds of materials that would be ideal for the flex sensor. So porous materials like some sandstones and pumice can be incompatible with common contact agents. For example, they might absorb all the water that you might put in contact with them, which is fine if you're looking at measuring their thermal properties when they're fully saturated. But if you wanted to measure their effective thermal conductivity in a dry condition, that can be inconvenient or difficult. These materials tend to be too hard and rigid to accept a TLS sensor, which would usually be your other option if you're looking at a material that is incompatible with contact agents. So the flexibility of the Flex TPS sensor really comes in handy for dealing with these kinds of materials. So when you're testing a sample with these kinds of materials, you basically sandwich your sample around the sensor and then apply clamping force or contact force to control for the contact resistance. But you don't need any contact agent. So as an analog to some of the porous geological materials, we'll look at a slab of concrete, which we basically just cut in half, and then we mount the sensor, as you can see in the image here. Thermal conductivity can be characterized in different samples of the same deposit, or it can be the same sample can be tested in multiple locations within the sample to understand the material's variability. So for the concrete, we did the multiple locations within the same sample approach, and you can see that the relative standard deviation of the 10 different locations that were tested was about 3%. So pretty consistent for a concrete material. So we'll highlight a few materials that this method would be very appropriate for and their typical thermal conductivity ranges. So pumice, for example, on the low end, I've seen reports for some highly porous pumices as low as 0.1 watt per meter Kelvin. And on the high end, I've seen as high as 1.4 watt per meter Kelvin. So that's over a full order of magnitude in terms of the thermal conductivity range of this kind of a geological material. And it really highlights why you need to make sure that you're testing your actual materials that you're looking to simulate or looking to run a process with. Because if you're using a book value in this case, you could be over 50% off. The effective thermal conductivity of these pumice stones depend on the moisture, the composition of the pumice itself, and the porosity. When you're dealing with the thermal conductivity range of, or when you're dealing with other porous materials like sandstone, the same sort of principles apply. So sandstone is not quite as variable as pumice, but it still has about a 2x factor of variability depending on the type of sandstone that you're looking at. As with the pumice, the effective thermal conductivity depends on the moisture, the composition, and the porosity of the sandstone deposit in question. So it's very important to make sure that you're characterizing the local sandstone's thermal properties if you're running any sort of a process that requires some thermal management. The final sample type that we'll highlight here is volcanic tuff. So in this case, the typical thermal conductivity range, again, it spans a full order of magnitude from a low of around 0.4 watt per meter Kelvin to a high of around 4 watt per meter Kelvin. And because this sort of materials moisture level, composition, and porosity can vary so much. The thermal conductivity range can also vary by a relatively large amount. So that's why it's very important for any kind of geological application that you test the local deposits' thermal properties, because the book value, if you look it up, the error bars on those values, the uncertainty levels are quite high due to the inherent variability of geological materials. The final set of application examples would be the line source, transient line source or needle probe sensor. And this is a method that's ideal for testing semi-solids, very viscous materials like bituminous oil sands if they're very soft, or if it's also good for testing unconsolidated materials like sands or gravels. It's not really suitable for lower viscosity fluids because you'll get some convection issues. And it's not really recommended for rigid solids due to the potential to damage the sensor when you try to insert it, and also due to thermal contact resistance issues. For rigid solids, we would recommend either the modified transient plane source or the transient plane source, depending on the user's application. Transient line source conforms to a number of ASTM and IEEE standards, as you can see on the slide here. So for transient line source, the principles of operation of this one, of this test method, are fairly straightforward. The method approximates the heater, or the heat source in this case, as a infinitely thin straight line. So in a real world scenario, you have a finite length of the heater wire, and in the middle of that heater wire, you place your first thermocouple junction. And then at the end of the needle, you place your second thermocouple junction, and you monitor the temperature difference between those two junctions as a function of time. When you express the temperature change as a function of the natural logarithm of time, you'll see a region which is non-linear at the beginning, and that's basically allowing the power flow out of the line source heater to stabilize, and the contact resistance effects to stabilize. Then you'll get to a linear section, and this is the section that you actually analyze. Eventually, the plot will become nonlinear and begin to deviate from linearity again. And this can be due to a number of issues. The first one being that perhaps the whole system is starting to approach steady state, because the ground is basically acting as an infinite medium in this case. So eventually it will begin to approach a steady state type of condition. Or it can be due to boundary effects if you're dealing with, for example, a core sample that you've taken. So the goal when you're analyzing this sort of data is to find that linear section and analyze it to get good quality test data. In all cases, C-Therm's software enables easy analysis of the data, and it performs all of the computations. In the modified transient plane source method, the data analysis is totally automated. So the user does not need to do any of the data analysis. They just get the test results in a table like you see here. In the case of the transient line source and transient plane source, some user input is required to analyze the data, but it's highly automated and intuitive in terms of how to use the software to get the good quality data. Looking at some transient line source applications in geological research, we'll look at the testing of gravel with the transient line source sensor. You can see here the gravel material, and the thermal conductivity which we measured on this particular type of gravel was 0.75 watt per meter Kelvin. with a relative standard deviation of about 0.4%. You can also look at soils with this test method according to both ASTM V5334 and IEEE 442. When you're testing with this sensor, you can place the sensor directly into the soil, or you can remove some samples and bring them back to the lab for testing at a later time. This slide shows the thermal conductivity of topsoil, both dry topsoil and also loaded with 50 weight% of water. So you can see the thermal conductivity increases by a factor of 100% basically, up with the addition of 50 weight% of water. This just shows how moisture content, when you're testing, especially unconsolidated geological samples, can have a very dramatic effect on the effective thermal conductivity of a sample. And this is looking at the IEEE standard, looking at the thermal resistivity expressed in degrees Celsius times centimeter per watt of the topsoil. Again, looking at the dry and also the wetted topsoil material. All right, so that basically sums up all of the data that we were hoping to cover during this webinar. So at this point, I'll turn things over to Adam so we can wrap up and then open up the Q&A session.
Excellent. Great review, Sarah. Thank you very much for taking us through a lot of content on the different variety of geological sample formats and different situations. I think it's very apparent in your presentation that there is a broad range of sample formats and the benefits to having a versatile solution with different methods to match up to those situations. So next week, Thursday, April 23rd, we do have a webinar focused on phase change materials. I see a few of you have already entered in the chat box that you would like to register for that. That's wonderful. Be very pleased to have you online with us. We will send out a note on this upcoming webinar as well, but would love to have you join us online for that. If anyone on the call has found this really interesting and would like to receive a video demonstration of how the software works, how it actually operates. We're doing a lot of video demos, and I would just encourage you in the chat box, if this is an investment that you're considering and you'd like to set up, it could be as short as 15 minutes. We can have one of our application specialists that works with Sarah run you through an actual real-time measurement. We'll do some screen sharing so you can see the software run. We have a facility set up with cameras so that you can see live how the testing is completed, what it's like to interface with some of these different sensors. We didn't get into a lot of the software's aspect of running the measurement. This is more theory and application. But we are able to demonstrate that, no problem. And it's a little bit more difficult to get there in person. Usually we would like to bring a system in for a demo and show you, but a video demo is the next best thing. And in today's climate, it makes a great option to get more familiar with the technology. So if you'd like a video demo, maybe just put in video in the chat box. And Stuart will be providing a link to where you can request a quote. So if anything here was of interest and you'd like a quote prepared for you, we'd be happy to have that prepared. Certainly, it can be helpful if you're just trying to get a sense of budget, what the investment looks like. We can be happy to prepare that for you. So let's just advance it to the next slide, please. So we want to thank everyone for joining us today. We're coming up on the hour, so I think we did a good job of working through a lot of material very quickly, all to the credit of Sarah. So thank you very much, Sarah. Great job. At this point, we're going to move into the Q&A session. I see a lot of great questions populate our chat board. So we're going to pick our way through that. So Sarah, if you just want to advance the last slide, we'll start with that Q&A session. But at this point, I typically stop the recording. So for those of you listening to the recording, thank you again. And we'd be happy to pick that up on a one-to-one discussion. For anybody that would like to stay on the line for the Q&A session, we're going to work through the questions in the chat box.